And welcome everybody to lesson number 3, the actual building blocks inside of BGP. What makes it all possible, how does it work, and this is what we're going to discuss right now. The reason this is so important is because configuring BGP is actually pretty simple. The commands, typing it in, not a real big deal. Understanding how the components are working behind the scenes, extremely important, not only for the real world and troubleshooting, but also to make sure as you design networks and implement them and test them that you know what you're looking for and what you're looking at. So we're going to focus in this lesson on the actual components that make it all possible. We know that routes are shared from one autonomous system to the other, building the control plane. The reason we build the control plane is so that when a packet needs to be forwarded, the router knows how to make a forwarding decision. So what is the actual data structure, the elements, if you will, that go into Border Gateway Protocol, BGP? Well, it's going to use 3 tables. Those 3 tables are a neighbor table. It keeps track of who its neighbors are. Like Mr. Rogers, won't you please, won't you be my neighbor? So once it knows who the neighbors are, for example, maybe there's a neighbor in Autonomous System 89 and another neighbor in Autonomous System 2, for example, and they find out who the neighbors are and they say great, and that's established on TCP port 179. At least one side is. So when they establish their connection, they build this neighborship. Then they get updates from each other. So AS89 says here's my routes, and AS3 says here's my routes, and they all learn from each other. And then once we've learned the routes, then we consider locally on a router by router basis which ones of these routes, if I received multiple routes to get to the 999 network, which of all those learned routes is the best one. And then possibly, once after BGP has determined what the BGP best route is, then it gets put into the actual routing table, maybe. Now the routing table, when you do a show IP route, that's the global routing table. Not everybody gets in. As you know, if there's 2 routing protocols, EIGRP and RIP, and they're competing for the exact same network, the same network doesn't go in twice. If the same exact length, same network is shown up by RIP and EIGRP, EIGRP internal AD is 90. With RIP it's 120, and may the lower administrative distance win. Well, what if EIGRP and RIP and BGP are all competing for this one specific route? Who's going to win? Well, at that point, once BGP has figured out its best route and RIP is offering its contribution, EIGRP, then it's going to be up to administrative distance to determine from the global routing table which one actually goes into the routing table. So that's how it all pieces and parts together. So let's take a look at the specifics. First of all, before you can have a neighbor, you have to go ahead and establish a neighborship. And so it doesn't happen automatically. It's not like RIP or EIGRP or OSPF where a router starts saying, hey, I'm doing this, and if your parameters match, let's be neighbors. With BGP, you have to specifically specify who your peers are. And you know, peers can be good things or bad things, but in BGP, unless you specify who that peer is going to be, and that other peer has also specified that he's willing to peer with you, the BGP neighborship won't happen. Once you establish a neighborship, then you can start exchanging routes. And then once you get the route from the BGP neighbor, then you can determine which one of all my neighbors' routes advertising the same network is the best from a BGP perspective. And as we just mentioned, then you can put the best of all the routes into the global routing table based primarily on administrative distance if there's a conflict at that point. So how do we get the neighborship going? Well, it all starts with a plan. We want to identify who's going to be a neighbor with whom. And as Abraham Lincoln said, when you're going to implement BGP, Border Gateway Protocol, and you have 10 hours to do it, you should spend 9 hours planning it out, and then 1 hour in implementation. Now, he actually said that regarding a tree. If you're going to set up, cut down a tree, you should spend 9 hours sharpening your axe, 1 hour in implementation. Same is true here. We want to make sure we know exactly what our plan is before we just start throwing in commands, because just throwing in commands is not too helpful. So let me take you over to a live demo, and let me walk you through. Oops, let me actually change that, and let me bring you to a different screen. One moment. Hit the wrong button. Wow, I am like totally in a different space here. And I want to go to a different space, but this is not letting me. Hold on one second. It's going to be worth it. I'll tell you what I'll do. I'm going to just do it from right here and it'll be fine. So let me go ahead and share my computer screen. Sorry about that. That was interesting. I don't think I've ever clicked that button before. All right. All right, so now you're doing a live demo of my actual screen here. So as far as the building block goes, we've taken a look at the concept of a neighbor table, the BGP table, and the routing table. I'd like you to take you on a little tour out to the internet for a moment. And I have a looking glass set up. Looking glass is just basically a router that has BGP configured that you can get onto without doing any damage. So I've got some basic commands here in user mode that we can work with. So the first thing I want to share with you is the actual neighbors. How do you see who the neighbors are of this specific router that we're looking at? And the answer is you can do a show. Let me change my student view to full screen as well. Perfect. I'm going to do a show IP BGP summary, and that is one way of viewing that information. So here's all the neighbors, actually one page of them. It looks like he has a boatload of neighbors. You have the IP address on the left-hand side, and then we have the autonomous system number, how many messages we've received from that puppy, how many we've sent, the table version. Let's see here, that's 720,000. That's a lot. That's way up there. This is the input queue and outbound queue. So there may be a situation where we need to send a whole bunch of updates, and we have to wait a few moments to do it. We keep those in queue for the next batch of updates we're going to send. Those are also limited on the internet, so we don't just send them every millisecond that we get updates. And he's been up for 3 weeks and 0 days, and this router has received 321,834 routes from that neighbor. And he has a lot of neighbors. So that's the BGP table for this device. So that's that. Okay, I'm sorry, this is the neighbor table, excuse me. I'm adjusting my other screen here. All right, so if we wanted to take a look at the routes we've learned from these devices, we could go ahead and do a show IP BGP, and that will show us all of the BGP learned routes in the BGP table. This isn't the routing table yet, it's just the BGP table. And here we have a whole boatload of routes. Let me just do a page up. So this is saying that for this one prefix, the 1.11.128.0/17 network, all these neighbors from that highlighted area below have, I shouldn't say all these neighbors, we've learned this route that many different times. This value right here is the next hop. So that's the next hop of 207.172. That's the next hop. And the little check mark, the little greater than symbol right here indicates that the greater than symbol part indicates that this is the best out of all of them. So out of the 1.11.128 network that we've received from all these different neighbors, they're all advertising it, this one right here is the best. Wow. And the next hop is 195.66.232.239. That doesn't mean that's the actual neighbor who sent it to us. It's just that's the next hop that we should use if we want to forward a packet to that network. And it's also indicating that it went through, we learned this from AS5459, who learned it from 9318, who learned it from 3891, who learned it from 17839, and it's 17839 who sourced this route. If you'll notice, 17839 is the very last autonomous system listed in the string. This is why it's called path vector. It's keeping track of all the autonomous systems that this specific route has gone through. And one of the items to decide on the best path, just one of them, is the AS path length. So here we have 4, but we also have 4 on a couple others. If we want to take a closer look at that route, we could do a show IP BGP and just put in that actual route. And the actual route is this guy up here, the 1.11 network. The show IP BGP for that one route, and it's going to give us all the details on it. We're going to spend a lot of time looking at these, but here in the building block component, let's see, here's the best one right here. So this is the one he chose as the best. Here's the AS path. It was sourced based on an IGP, probably a network statement on the router who sourced it. Local preference is 100 by default. It's a valid route, meaning we have a route to the next hop, and it's considered the best. It also has some community values. So we'll take a closer look at why this router decided that specific route was the best out of all the choices it had. But that's an example of the BGP table. The last thing I want to share with you here in this BGP building block section, as far as the live internet is concerned, is if we do a show IP route, and I'm going to limit it just to BGP, this is the actual winners table. So out of all the routes that we've learned via BGP, only a few of them are going to make it to the routing table. For example, for this one specific network, the best path, where was it? Right here, has a next hop of 195.66.232.239. So if we actually did a show IP route BGP and did a pipe and said include just that, we wouldn't have to look at the entire routing table in this puppy, which might be not so bad. Okay, well, he has that next hop is good for a lot of routes, including the one I just looked at. I guess I should have filtered on the route itself. Let's do that. Let me, what was that network? Let me just scroll up and get the network. The network in question was this guy. Copy him. A show IP route, and we'll include just that one specific route, not the next hop. Show IP BGB. Almost got it. Let me just fix that typo. Alright, so for that one route, 1.11.128, as it sorts through its huge routing table, we can see that, there it is right there. Alright, and there's the next hop based on, and it's a BGP learned route. So, the overview that I wanted to share with you is that we have neighbors, we learn routes from those neighbors, we figure out the best possible BGP routes that they've shared with us, and then based on that information, we put it possibly inside the routing table itself. This could have lost, by the way, if we had learned this route through a static route. A static route has an AD of 1, I believe, as opposed to 20. So as a result, we could possibly have not put this route inside of the actual routing table if there had been a better option for us. Alright, so that's the global routing table. We take a look at the BGP. We took a look at the peers as well. Let's take a quick look at what they do to become a neighbor. Two devices when they want to become a neighbor with each other. Right here. So BGP does not have its own protocol. Now OSPF, it does have its own layer 4 protocol. EIGRP has its own layer 4 protocol. RIP borrows UDP. BGP borrows TCP. So when two neighbors want to pair up and be friends, what they're going to do is they're going to neighbor up and basically use TCP. There's going to be one side that's going to be a client and one guy's going to be a server, and that's how it operates. So the person who initiates the connection, who says, I want to be a neighbor with you, is going to initiate on some high numbered port, for example, something higher than 1024, and it's going to make the connection request a hello message over to the port 179 on the device it's trying to become a neighbor with. And then the session, once it's established, is going to be TCP. One side's going to be 179 and the other side's going to be the high random port number that the client initiated from. So either device could actually initiate a session unless you have access lists or something else that might be filtering that. So we use port 179. You have to manually configure neighborships based on a neighbor statement, and it's not directly connected. You don't have to have a route. You don't have to have a specific neighbor on the same local network, which is different than the IGPs. For example, take a look at our diagram. If we wanted to, let's say our physical connections for R8 to R6, and then I'm going to draw some physical connections here. Let's say we have connections here, and let's just say that let's say AS3 is going away for a second. We can do that. So we'll take out AS3. And our physical connections are like this. And that was the eraser tool still. Excuse me on that. Our physical connections are like this. And if we wanted R8 to be a peer with R4, and these are our physical connections again, we could do it. We just tell R8 you're going to be a neighbor with, let's say that's 10.45.0.0. And this guy is .4. And up here, this guy is .8 on this network right there. So what we could do is simply tell R8, you're going to be a neighbor with 192.168. We can tell R4, he's going to be a neighbor with 192.168.68.8. And tell R8, it's going to be a neighbor with 10.45.0.4. And as long as TCP was allowed, specifically destination port 179 for the session to set up, that traffic would be okay, and they would set up a neighborship. So neighbors do not have to be located on the same physical subnet. Now for external neighborships, they often are, but it's not required to do so. So that's one significant difference as well. Also, as far as the types of neighborships, let's take a look at that for a moment. Let me bring up a new diagram. That one again. If we have a neighborship, let's go green. Anytime you have two neighbors that are in the same autonomous system, so let's say this network is the 192.168, I'm going to move down .89.0 network between R8 and R9. R8 and R9 could simply tell it, configure both sides and say R8 could say R9's a neighbor and he's in 89, and my local autonomous system number for router BGP is 89, and R9 could do the same for R8, and as a result, that would be an internal BGP neighborship. When R8 establishes a neighborship with R6, the commands are identical, absolutely identical, with the exception of R8's router process is 89, and he is connecting to R6, and R8 is saying, hey, R6 belongs to the autonomous system 3. That's the only difference in the configuration of internal versus external BGP, is that these IDs right here, so AS89 and this guy's AS3, they're different. And as a result, that's what makes the external BGP neighborship an external BGP neighborship. So the router 8 would say, what's my local AS number? What is the AS number of R6, which is AS3, and as a result, it would know that this session right here is going to be external BGP, just like that. So once we set up the neighborships, which we're going to do in the next lesson, what exactly do they do with those neighborships? What is the language of love that these devices use to talk to each other, whether it's internal or external BGP? And here's the 4 message types, packet types, that they're going to have between each other. And they're really important, and they're really simple. An open message. Now, what an open message does for a living is says, hey, I'd like to introduce myself. I'm R8, my autonomous system number is 89, and I'd like to be your BGP neighbor. Now, R6, when he gets an open message, if we go back to the diagram, when R6 gets an open message, if R6 is configured with a neighbor statement that points to R8, that says R8 is in AS89, there's a good chance that neighborship is going to come up, assuming TCP is being allowed back and forth. It's that simple. So an open message is simply introducing yourself, saying, hi, how are you? Now there's also some back and forth that happens when an open message is sent. We also share some capabilities like, hey, what can you do? I can do VPN v4. I can do route refresh. I can do outbound route filtering, etc., etc., etc. They're going to announce also their capabilities during this open conversation. Then once they have a session established, they're going to send keep alives. By default, the keep alives happen every 60 seconds. And the dead timer is 3 times that. So if the hold interval is 180 seconds and they negotiate that, they're going to do keep alives at 1/3 of that, which is 60 seconds. And we can control that, but that's the default. So it's a TCP keep alive that you'll see going back and forth every 60 seconds between these guys just to make sure that they're happy, and up. An update message, let's think what that could be. An update message, oh, I get it. If a route has to be advertised, for example, if we go back to our diagram, if R8 wants to share a route, a prefix, with R6, maybe he's sharing the 192.168.89 network, or maybe it's sharing its loopback 8888. Either way, it sends update messages from R8 to R6 and saying, hey, I've got this great network, I just want to tell you all about it. Now, when it tells it all about it, it's going to include a bunch of information regarding path attributes that'll be help R6 in that decision-making process. I'm getting a little bit ahead of myself. Let's take one of these at a time. In the open message, here's what's going to be in the open message when we first say, hey, how are you? We're going to have what version of BGP we're running. The version on the internet right now is BGP version 4. What our local autonomous system number is, our local router ID, which, by the way, is the highest loopback IP address on the router when BGP begins. What if you don't have a loopback? Well, if you don't have a loopback, it's going to be the highest IP address on any physical interface. What if you don't have any physical interfaces with IP addresses? Then you're not speaking BGP. If you don't have any, I guess logical or physical interfaces with IP addresses, it's done. But that's what the BGP router ID is all about. What I would recommend strongly is hard coding the router ID. So instead of just changing a loopback in the future and your BGP router ID changes, if you hard code it in the BGP router config section, you'll never have to worry about it changing. That's a good best practice that we'll do as we lab this up. The hold time, as we talked about, is negotiated during this open message, and also the options, what I'm capable of doing. What I'd like to do, let's do this. I'm a big fan of protocol analyzers. Back in the 80s, when a protocol analyzer cost like $20,000 and now you can get them for free. I've always been a big fan of actually proving or taking a look at what's going on inside the wire just to verify that it's really doing what I think it's doing. So I've included some Wireshark inside of this presentation. I also have these captures that we can do live if we so desire. This is a BGP open message. Let's just take a look at a few elements. Under the capabilities, let's do this. Multi-protocol extensions, capabilities advertised. Take a look at the, I can actually draw on this, can't I? I can tools and comment and markup and give me a pencil. There we go. So I can mark this up. So right here, this device is saying I have the ability to do route refresh. Now what's that all about? Well, the cool thing is that in a test environment you can do clear IP BGP asterisk, and it totally wipes out any existing sessions that you might have with BGP. Why is that life-threatening in the real world? Because if you do that in a service provider network and you totally wipe out all your neighborships, that could be a resume producing event. Not good. Route refresh allows us to do soft refreshes of the routing updates. And that way you cannot have to break the TCP session, but simply gently request the updates again from a neighbor. And you can do that inbound or outbound. And with current iOS, that is a feature that's enabled by default. So in the hello message, they negotiate that. So there's the route refresh capability. And it also has here, for example, my AS number right here. So this is obviously coming from either router 8 or router 9. If we look at the actual router ID, I would guess that it's router 9. That's probably a loopback on router 9, or it could be hard-coded. The hold time is 180 seconds, and as a result, we're going to divide that by 3, and that will be our keep alive. If two devices negotiate different times, like one says 180, the other says 160 or whatever, they will choose the lowest and use that. So that is one parameter that they don't have to match on perfectly. So that's the details of a hello message. As far as the keep alives, let's take a look at that one next. The keep alives, they're really simple. We simply have keep alive that goes out every 60 seconds. If I'm your neighbor and I don't see a keep alive message based on the hold time divided by 3 that we agreed to, I'm not going to give up on you immediately, but I will give up on you after 3 of those hold time interval passes. So if my hold time is 180 seconds and I haven't seen any advertisements from you in 180 seconds, I'm going to declare the session dead, tear it down, and it's off the map. So that's how we certainly would get out of a deal with a neighbor. We stop becoming peers. As far as the actual updates that are being sent, those are pretty cool as well. The updates include information such as networks, like, hey, here's the 25 network, here's the 26 network, here's all of the path attributes. You know, when we looked at the BGP table and it had all that information on next hop, had information on the AS paths, it had information on the origin code for that route. All those are attributes that are sent inside the updates. Now, an update doesn't always have to be good news. An update could say, I'm withdrawing this route. That used to be a good route for me, no longer is, I'm going to take it back. So updates can have withdrawals. Like, I missed that route. Well, it's a good thing to communicate. It can have updates as far as new information or updated route information. And the path vector attributes is talking about things like the multi-exit discriminator, the AS path, the origin code, and all these attributes that we're going to focus on in session 11, 12, 13, and 14 that we can use to manipulate the actual BGP. So, you know, the funny thing is, too, they're called AS path attributes, and one of the path attributes is called AS path. So we'll cover that, too, and make sure you're clear on that. What does one of these BGP updates look like? I'm glad you asked. It looks something like this. So this is an update message, and if we go through and get my tool out again here, so I'll go to Tools and Markup and grab my pencil, which is still on. Great. I've got my pencil available. Let's take a look. We have the path attributes of origin, so we're going to do a little preloading here. Origin is how that route got into the BGP table. So if we go back to, I think I still have it up, if we go back to this right here, oh, he's down. That's okay. I'll show IP BGP. So right here on the right-hand side, this is specifying how that route got into BGP. And the I represents, it got into an IGP. So the I on the far right represents this I right here. What does that mean, IGP? It means somewhere, somehow, a BGP speaker probably used a network statement and added a route into BGP with a network statement compared to a redistribute command. So if they did a redistribute back here, it would have a question mark instead of an I. So that's the attribute we're talking about with the origin code. So that's being sent. If we expanded these, they would show us what they are. The AS path, look at that. Oh my goodness. In the AS path, it's all the autonomous systems that we've gone through. Oops, let me go of that. The AS path is all the autonomous systems that we've gone through. So if we go back here to our diagram, for our output, down here it's showing that this route right here, which is the 123.2.0.0/21 network, has gone through these autonomous systems. It started in 208, that's where it was injected via a network statement into BGP. It then got passed to 6783. It then went its way to AS22, and then we learned this from a device in AS11. That's what this specific highlighted information is. And that's the AS path attribute. So it's a component of all the attributes of the updates we can get. Let's go back here. The next hop, we've already talked about that for a moment, but the next hop is the next hop we're going to use if we ever need to forward a transit packet to that. So that's the next hop attribute. Again, we can go back and look at it, but we've seen it a couple of times. So if this route is the best one, based on all the BGP routes that we've learned, and there's no other competition, we're going to inject this route into the routing table and the next hop is going to be specified in this case as 192.168.89.9. The multi-exit discriminator is going to be advertised as well. Now the AS path up here, by the way, see how it's empty? And that's because we're advertising this network to an internal BGP peer, and it's our own network. So if we're sourcing a route and advertising it to a neighbor who's also in the same autonomous system, we're not going to prepend or anything else. It's simply going to be, this is a route that's local to our AS. That's why it's empty. Multi-exit discriminator, right there, that is also called the metric. So if we went back and looked at our, let's actually go out to the internet again, because they're going to have some that are going to be very interesting. So let's connection out to here again. To show IP BGP, and the actual metric value, or the MED, the multi-exit discriminator, is represented by this column right. So that is the value of the metric. You notice that some of the routes have different values. The lower is the better. If we're comparing the metric, or the MED as they call it, multi-exit discriminator, lower is better. That's if we're comparing it, and we'll discuss all that as well as how that operates. But that's the actual MED value. So moving back here, then we have local preference as well. Local preference is being advertised to internal BGP neighbors. It's never advertised to external BGP neighbors. But we also have a default for local preference. So we'll discuss how that operates. But here's the secret to this. All of these path attributes are simply attributes describing this route right there. Basically, anybody who gets this update is going to say, okay, great, to get to the 999 network /24, all these attributes of origin, AS path, next hop, multi-exit discriminator, local preference, I'm going to take all those and put them in my BGP table, and then, assuming I can reach the next hop, I'm going to compare all of the attributes I received from this neighbor, from this update, to that same prefix received from another neighbor, and I'm going to use all of those attributes to decide which one of the two routes from neighbor A or neighbor B is the absolute best. And then it puts that as the winner inside of BGP, and then the winner from BGP, the best route, again has the possibility of making it into the actual routing table itself. Okay, what if we need to get rid of a route? This is an update saying, hey, this update is, a new information. If we need to withdraw a route, it would be another BGP update, BGP message. It's called it's still an update, but we're actually, this time we're taking out a route. So as good as that route was, now we're saying, oh, by the way, that 999 network I told you about, in the previous update, I'm withdrawing it. So go ahead and remove me as a possible source for that information. And if you hear it from somebody else, more power to you. So that's a withdrawal. If you have a situation where two BGP speakers are talking to each other, they're having a great time, they're just laughing it up, yucking it up, and everything else, and then all of a sudden R6 is powered off, we'll just power him off, and he doesn't send a goodbye message, R8 is going to send these little keep alives every 60 seconds by default. At the end of 180 seconds, 3 missed keep alives, it's then going to say, you know what, this is over. And it's going to actually send a notification message saying, it's been fun, it's been real, goodbye. We also could have a situation where R6 is configured for AS40, and R8 thinks it should be AS3, and as a result, they don't match up. So they do the three-way handshake with TCP, they start to try to neighbor up, and then they're sent a notification message to each other saying, hey, you know what, you're not in the right AS, I'm closing off this conversation. That message would look something like a notification. So there's there's 4 types of packets that we've talked about. We have the actual hello that's being used to communicate initially, to say, I want to be your buddy. We have the, what's called an open message. We have the keep alives, we have the updates, and now we have the notification. And examples of why are listed right here. The timer times out, the hello, the hold timer times out. you have the wrong autonomous system. There's a misconfiguration. You support a feature that I don't support, and it's critical, like, for example, IPv4 support, and you don't support it, and as a result, I'm not going to become a neighbor with you. A notification message would look something like this. So it'd have an error code, and in this case, a reason. So in this example, we have the error code of hold timer expired. I manufactured that. I set a really short hold timer and I shut one peer down. I actually closed the interface and then I just waited for it to happen so I could generate this and collect a snapshot as well. So when a neighbor actually sets up, let's actually do this. There are several things that go on for the actual connection between two BGP neighbors, and it's called the the peering states they go through. So let's say you did a debug and you wanted to watch all this. Here's what would happen. Now, why is this important? Because stuff goes on, stuff happens in the real world, and stuff doesn't work all the time. And if it fails, you don't want to just sit there and say, I wonder why it failed. I'll just try it again, and I'll try it again, and by understanding what's going on behind the scenes, we have a better understanding what we need to do to resolve it. So if we did a show IP BGP summary, I think we should do that real quick. So we lost our internet router again, so I'll bring it back up. Show IP BGP summary. This will give us a really good sampling of the different states that a device might be in. So it's thinking about it. Thank you very much. And okay, here we go. So under the state prefix heading, it's either going to list the number of prefix received, which is a really good sign, by the way. If you have the established state, three-way handshake took place, the hello worked out, the open message worked out, they exchanged capabilities, and they went to established state, what you're going to see in state/prefix received is the number of prefix, an integer that's sitting there. If you're something like this, you're thinking, holy cow, what's going on with that? We haven't had any. Look at all the messages received and sent. We've never been up with this neighbor, and we've never succeeded in the open messages between the two of us. We haven't gone to established. Let's see if we can find one more. Oh, look at this one. Idle. I love it. So we have active, not good. It means it's actively trying to get a connection. We have idle, which means it's not even trying to get a connection. And then we have these numbers, which represent how many prefixes we've learned from that specific peer. So now that we're armed with what it looks like in the real world, let's take a look at what those mean. Idle says I'm waiting to start the three-way handshake. Now what would cause that? You don't have a route. A router doesn't have a route to the peer's IP address. If it can't reach it, there's no route to get there, it's not going to even try to do the three-way handshake. There's also an issue with external BGP neighbors where the TTL is too great. You're not directly connected. We'll talk about that in a little bit. So that would be issues for the idle state. The connect. You've done a three-way handshake or you're waiting to complete the three-way handshake. It's not working out. So you're most likely going to see idle or active if there's an issue. You won't often see the connect state because it's actually trying to establish, and it goes almost immediately to active, meaning I've tried the three-way handshake, it took like 2 milliseconds, and now I'm simply trying to connect and it's not happening. Open sent is when the one side has sent our open message saying, hey, I'd like to chat with you and here are all my capabilities. Once we do the open sent, we're going to do an open confirm once we get the open message from the other side saying what he can do and we agree to it all. So after the open confirm, we then move to the established state. And what you should see, again, is the number of actual IP prefixes learned from that peer. If you see prefixes learned 0, that's a good sign. It means he's got nothing to share. It's okay, but it's not active, it's not idle, and you've actually got a good session in place. So let's go to a router, and let's actually look at this. I think that'll actually make it. We won't do it on this router because that's an internet router, and I don't have access to that to change anything. But I do have on this local network. So we'll take R6 and we'll do a clear IP BGP, and we'll do it for neighbor. Let's do a neighbor. Let's see who our neighbors are. So just so we're all on the same sheet of music. So I'm on R6 at the moment, and on R6 has a external BGP neighborship with R8, and I'm just going to tell R6 to clear the entire BGP session, not soft reset, but a hard reset, the kind that would get you fired at a service provider. And he'll break the TCP session, and then we can watch, we'll do a debug, and we can watch every step as they build the session back to each other. So let's go back to our window here. Right, and on R6, we'll do a show IP BGP neighbors. Actually, do a summary, that'll work. So there's our neighbor. I'm going to copy his IP address so I don't typo it. We'll go into configuration mode. Actually, I'm going to stay right here. Debug IP BGP. I'm going to do a clear IP BGP, put in that neighbor address, and press enter. And it'll do a hard reset. So let's, I'll undebug this. And there's all of our information. So let's take a look at the pieces and parts. The first thing we have happen here is we were in idle state. And it went from idle to active, which is doing the three-way handshake. And then here we sent our open. So we sent our open message and we sent all of our capabilities. We said, hey, in my open message, I'm autonomous system number 3, and I've got the abilities to do, let's see here, here's some capability codes which we'd have to look up. But here's some that we can actually read. Check this out. Open has route refresh capability that allows us to do clear IP BGP neighbor soft, which just refreshes the routes instead of clearing the TCP connection. And there's also in the capability they're supporting IPv4. If we supported VPN v4 as well for MPLS, those capabilities would also show up in the open message. And so it went from open. Where's open sent? It's right here. Sending open, receive open, open capability. Okay, I can't find the other open sent. It's in this output somewhere. But here's, it went to open sent. So after it sends an open, it then goes to open sent. Waits for the neighbor to do their open. We negotiate and agree to the parameters, and then we go to open confirm. And then from open to confirm, where everything agrees, we'll then go to established. And now we have our neighbor session with that peer. And there it is again, which I didn't mean to do. All right, let's do this. We'll go to router BGP3, which is what I'm in. I'm going to say neighbor. Grab this neighbor. I'm going to say shutdown. And show IP BGP summary, just the output. So here it shows idle. And it shows on the right-hand side, in parentheses, administratively configured shutdown. So if you need to turn off a neighbor for any purpose, that's one way of doing it without just totally removing the config. Because once you remove the neighbor statement, you're also going to remove some other things that hinge upon that neighbor statement that you might want to leave there. So to bring back to life, router correctly. Router BGP3, and I just take that shutdown command and do a no shutdown. And then he's going to pop back up. And now we've received 6 prefixes from him. All right. So that's it as far as the building blocks for setting up or for working with BGP. Now the building blocks are the neighbors sending hello messages, setting up TCP sessions, being able to send updates, doing withdrawals, and withdrawal sounds bad, and also notification messages. Again, all this on the session of TCP 179. So if we want to see that, we do a show TCP brief, and it will show us the sessions that are in place. So to our neighbor of 192.168.68.6. Oh, that's us. Okay, so what we've done is we've established, we use the high order port 35,878 to connect over to R8 to destination port 179 on TCP, and we're in established state, and that's our session that we're using for that conversation. It looks like we also have a BGP session from us to R5, but see, R5 started this one. R5 used a high order port, and he connected to us on port 179, and that's our BGP session over to R5. And that's it. So in our next session, we're going to take a look at actually configuring BGP. We're going to do internal BGP, external BGP, and build it one step at a time. And so what I'm going to do during the break is I'm going to remove all the BGP from Autonomous System 3 so that we can actually go through the entire step by step. Thanks everybody. I'll see you in the next session.